said that they are spending too long to learn chapter 5. And chapter 6, I didn't manage to get what I wanted anyway. It was a little in a rush.
What is the end of chapter 3?
Chapter 3, all those problems that we had to cross the river, but there was no acceleration. And those problems also, similar problems also from the web of time. These are the kind of chapter 3s. I think it's called relative motion.
Not but the beginning of chapter 3, was that the like adding different triangles together or polygons?
Triangles. It's like when you have the river and you want to cross.
Right.
You get here, but the current carries you here.
Right.
This is kind of triangle.
Okay, that's
Anyway, any problem that involves x and y, but on the plane, without gravity, that's chapter 3. Anyway, but we will talk about it. All right, so we started talking about chapter 6. We talked about work. What is work? What is the equation for work?
Parallel force.
Yes, the force, but only the force that is parallel to the displacement, right? And since I just want the parallel one, that's why this cosine shows up. The problem where the woman was trying to drag that box, we only care about the component of that force along that displacement. So what we are going to do now is solving this problem of the box. The woman is trying to drag this box, and but we are going to try to find the work done by each force that shows up in this box. So let's try to make this box a little bigger. And this is the next slide. So this is the slide. I'm making a better drawing here. So this woman is trying to drag this box from this position to this position. So this is the G, the displacement. Let's read the problem. They say that the person pulls this crate, this box, 40 meters. So this D here is 40 meters. Okay. They also give us the mass of the box, the crate, 50 kilograms. And they tell us about all the forces. One is already showing up in the drawing. So we have this force here. Is this force parallel or not to the displacement? Not. So we'll have to take into account that. That's why they are giving us this angle. The angle there is 37. There are other forces in this problem. They are telling us that there is this FP, they said, this 100 newtons. But there is also friction. Friction should show up in which direction?
The left.
Opposite. I'm trying to go to the right. Friction is opposite, parallel to the surface, to the left. And the value of this friction force we don't have to compute. So that's nice. They give us is 15 newtons. Okay. Any other force that should exist on this box?
Gravity and...
Yeah, they're always there, so I'm going to write. There is the mg here. There is the normal force perpendicular to the surface. Okay. And I can even compute that because they give me the math. So if I wanted, I could. All right. Now comes the question. They want to know what is the work by each force individually. Okay? By each force. So let me start with the work done by them. The one that we already talked about. The work from the P, from the force of pulling. What is the value? How would I compute?
You need to find the parallel one, so...
Very good. So it would be the FT cosine of 37. What else? Work times D, times the displacement. And D there is 40. So if we put all these numbers together, let's see what we get. $3,200 joules, right? Okay, so one part of the problem is done. We got the work done by that specific force. Yeah.
How do you know which force is what?
This is just just use that force and the D, which was the displacement.
Can you just explain again what you meant by like the force is parallel to?
So the woman is trying to bring this box from here to here. What helps her to bring this box from here to here? Only this component of the force.
Okay.
That component doesn't help her to move in the horizontal. So we only pick that component that is parallel to the displacement. All right. Now I want to compute the work of another one of these forces, specific force, and the one that I'm going to pick is friction. So I want to know what is the work done by the friction force. What should I do? The friction force
of friction.
is already there, 50. So I'm going to put the friction force, the number is there. What else? Work is force multiplied by displacement, so there is the D. Is there anything missing? Or anything that bothers you in this? Negative. Negative, you see, because the displacement is to the right, but the force is to the left. So this force is opposite to my displacement. That's why I need to put this minus there. So let me mark this minus. This minus is telling us that my force is not really parallel to the displacement. It's anti-parallel to my displacement. In other words, there is an angle. There is an angle between my displacement and my friction force. And what is this angle here? 180. So this minus 1 here is coming from cosine of 180. You don't need to write cosine of 180. You just see that the force is opposite to your displacement. You put a minus. All right. Okay. So it's not parallel. It's anti-parallel. That's why I put this minus. Okay. So I'm done with this other work that we wanted to compute. Okay. Now I want to focus on another force, the normal force. What is the work done by the normal force? Nothing. Zero. Why is she saying that?
No displacement.
Yeah, it's perpendicular to the displacement. So it's not helping me at all. So this is zero. And how about the work done by the weight, by the gravitational force?
Nothing.
Nothing. Again, perpendicular. So this is zero. Perpendicular means 90. Cosine of 90 degrees is zero. Alright? Okay, so now I computed the work for each one of those different forces. I can sum them all and get the net work. So if I sum them all, I can get the net work. And so that's the next question of the problem. Yeah, it's not exactly how it said, but what is the net work? I sum all of these works, and what should I get? Oh, I didn't give you the number for this one.
That's 2,000. Negative 2,000.
Negative 2,000.
So it's 1,200.
Very good. So what is the net work? What is the sum of all of these works? Is the 3,200 minus the 2,000. This will give us 1,200. So one way to get this net work is by summing those works that we computed. The other way to get the net work is find the net force along that displacement multiplied by the displacement. This is another way, another possibility. Okay, so here I sum the works for each force along the displacement, and here what I do is first compute the net force, then find the net force. Do you understand? So either
P cosine 37 and plus force of friction times D.
very good. So the net force would be just what you said, just as we do for Newton's equation. I put all the forces along the direction of the displacement. What is it? The force P cosine of 37 minus the friction. This gives me the net force. The net force multiplied by the displacement will give me also the net work. So I have two ways to do that. Either I sum the works, or I find the net force and then multiply by the displacement. It's pretty much the same thing.
Are we only using cosine because we're going like it's the x?
Because it's not because I'm concerned with this direction. So if they are giving me this angle, I want this force in this direction. So this direction here is adjacent to this angle. That's why we put a cosine.
But like I'm saying, for example, when you were explaining like why you don't do perpendicular or why the friction would be opposite, you said because perpendicular is cosine 90 and the other one's cosine 180. So where does that cosine?
There is yeah, you're right. There is a force here, which is FP sine of 37, but it doesn't help me. So I only put the ones that helped with that displacement. That one would also give me 0. Okay, so now a qualitative question. This one. What do we have? We are dragging that box, and just as that woman was doing before, and the question is, when she drags it just parallel to the surface, that's angle 0. Okay, so what will be? How does the work change as this angle changes from 0 all the way to 90 degrees? So in which case will I have the maximum work, and in which case I have the minimum work? So when I go from 0, is the work minimum or maximum? This is the displacement.
Maximum.
Is the maximum. Do you agree with what I'm saying?
Yeah.
This is the case where instead of this 30 degrees, she's dragging it like this. So perfect scenario. So 0, angle 0, maximum work. If she starts giving an angle, then she will get less and less work until if she gets perpendicular, well, she will get no work, there will be no displacement along the x. Okay. So from 0 to 90 means from maximum to 0. Yeah.
And if she's picking it up,
There's
there's still no displacement, even though she's even though there's displacement in the y. We still consider it like there's no work done.
Then there is work. There is work, but not along the x. There would be work up. That would be a different problem. In this case, let's assume that she's not strong enough to carry it. Okay, so she didn't move it up in the y. Okay, so now let's try to solve this problem. Let's see if we understand what they are saying. That thing that looks like a triangle is a hill. Okay, so I'm climbing a hill. A hiker is climbing the hill. And what we are doing is, here I am, and I'm just carrying a box. Okay, so this is my box, and I'm carrying it up the hill. But I'm moving at constant speed. Okay, I'm not pushing this box. There is no car. There is no bike. The speed does not change. I'm just going slowly, constant speed. So, if you focus on the box, what are the forces that exist on the box?
Fn. Normal force.
Fn because of the contact with my hands, yeah. And you see that in the drawing there, we are calling it Fa. It's the force that the hiker is exerting, or the force for holding. So that's this A.
Mg.
And mg, very good. Anything else?
Well, how are we showing the Fn with the hand? Are we not considering that?
That's a good one. There is a force Fn here. Now you complicated the problem. Yeah.
So it's not.
Yeah, there is a normal force with that. Some contact all around here. Okay, so there is.
Go out.
Yeah. But I still have to address the point. Okay, so I have here on the right and on the left my normal force. Normal force in this direction, normal force in this direction. So on the box they cancel, okay? So I'm not going to draw that because it doesn't help us with the problem. So these are the only two forces that I have. Okay, What else they tell us? If you read the problem, let's see, they give us the mass of this box. Okay, so let's write it there. 15 kilogram. They also give us the height of this hill. They don't give me this D, this is the whole displacement, but they give me this height. And this height is 10. So I'm moving at constant speed. If we are moving at constant speed, this box that I'm holding, I'm not pulling it up, I'm not throwing it up, it's just there all the time, and I'm going up with constant speed. What would you say about the relationship between this force and mg?
They cancel out.
They cancel. They have the same magnitude. So the force for me to hold this box, this F of the hiker, is equal to the weight. If I'm not strong enough, this will fall. If I apply a force that is bigger than the weight, what is going to happen? Poof, it's going to accelerate up. Okay, so it's not accelerating up, it's there. So this FH is equal to mg. In other words, if you prefer to use the equation that we had before from chapter 2, I'm summing all the forces, and this is equal to 0. I'm moving with constant speed. Okay, so this is an important thing. Alright, so now we stare at that, and we want to compute the work done by this force, and we want to compute the work done by this force. They didn't give me the value of this angle theta, but it shows up in the drawing. So I'm just going to put that angle theta there.
If they're equal, isn't the work the same?
Very good point. She's already anticipating what we are going to get, but what you're saying is the net work will be 0.
Yeah.
This is correct. But before I get to that point, I'm going to compute the work just caused by this force. And then I'll compute the work just caused by this force. And then I will sum all these works and see that they cancel. The net work becomes 0.
I understand that, but also, didn't you say like if the network was 0, there'd be no displacement?
The net. Okay.
Yeah, there's no displacement of the box in your hands.
I'm saying it's moving. I'm saying.
It is moving at constant speed. Yeah, you're good. There is no net work, and what is happening is the speed of this box is not changing. There you are. We are back to chapter 4. Let's remember chapter 4. If I have the net force being 0, does it mean that I'm not moving at all? Remember the elevator that we talked about last class?
You're not accelerating.
Very good. Okay? So if I do not have a net force, I'm not accelerating, but I could still be moving with a constant speed.
So is that the same thing here? Means there's no acceleration.
Exactly. There is no acceleration. That's why they keep writing. They wrote to the us there. The box is moving with constant speed. Okay? Laura, don't skip. I want to talk to you. So no acceleration, but I can still be moving, and we are moving with constant speed. So it makes sense that the net work is 0, net force is 0. Okay, now let's go one by one. Yeah, question.
But the other problem, like our next one, is also there's no acceleration.
In the other problem before, we didn't compute the acceleration, but yes, there is. In that problem before, this one, right? What we got was this net work. And there is a net force. So yes, there is an acceleration. We didn't compute. But this object there is increasing its speed, for sure. In this other problem with the hiker, no. The speed is constant. All right, very good. So let's go one by one now. We want to find first the work caused by that force of the hiker, the supporting force. What are we going to do here? If this angle is theta, what is this angle?
Theta.
Super
Fast.
sharp today, huh? Very good, right? These two are parallel, and this one is theta. Good. This is fun. This is going to help us with what? Why did I put
The
that
other
thing
angle. The one between MG and
Yeah, let me make this drawing a little better so nobody gets confused. This is our hill, right? And here's my box. And we put here the force for the hiker, and here the MG. And we just said that if that angle is theta, this angle is also theta, and this angle is also theta. So it's good to have that there. And it's good to have that there for what? We want to compute this work now. There is no friction. These are the only two forces involved in the problem. I want to get the force that is parallel to the displacement. This is the displacement. So how do I get the force that is parallel to the displacement? This is the force. Do you agree that this force
Cosine.
here is parallel to the displacement, which is a cosine?
Because we're finding the
Wait,
x.
could you say that again?
Let's look at this again. This is the force, all right? But I don't care about this whole thing. I only care about the part that is parallel to my displacement. So I'm making a triangle here, so I can decompose this force and select only the one that is parallel to the displacement. Parallel to the displacement is that FH, this is adjacent, so cosine of theta. Yes?
What did you just find?
This is the force, okay? Pointing up, my displacement is along this direction here. So I pick the component that is along this direction. So I make a triangle here to give me that force, and that is the cosine, is adjacent to the Good? So all that to come here and say, what I need is the adjacent. So this is the force part. What else do I need to get the work?
displacement.
The displacement, so that D.
Even
Here.
though theoretically the box is not moving in your hands.
It's not moving in my hands, but it's moving together with me, going
So
up
it does
the hill.
have velocity.
It has a speed, very good, but it's not accelerating. That speed is not increasing or decreasing. It's always the same.
Okay.
What else? What else do I need now? I'm just putting the symbols now. Let's go for the work done by the gravitational force, by the mg. What do I need to do there also?
Decompose.
We also need to decompose, right? We only want the component along the direction of the D. So I'm going to make my triangle here. This is the guy that I want. And this is what? Cosine or sine?
Cosine.
Again, cosine. Mg cosine of theta. Okay, so I'm going to put it there. I have here mg cosine of theta. What else do I need?
Do we have to put this on like an x and y axis or no?
If you want to talk about axis, yeah, you can say that this is your x-axis if you want. You don't need to call it. Yeah.
But isn't it
Is it
negative
like-
MG?
Yeah.
Ah, I'm
Doesn't-
waiting. Yeah.
Yeah.
Negative. Very good. Negative because it's against the displacement. And what else?
D.
Down.
Times okay.
Wait a second. We are talking about. We are going to get there. But here, I'm just talking about this force and this displacement d. So I put mg cosine of theta multiplied by the displacement d. But you anticipated something very good. Did you understand what we wrote here? Wait, this story of the high book. But did you understand what we wrote? We picked the components of the force that were along the displacement, so it was the F and the mg along the displacement. Computed the work for each one. The work for this one is here. The work for this one is here with a minus sign because the opposite by displacement. Good? Okay. Remember what we said? The net work is the sum of these two. Is the net work 0 as we had predicted?
Well,
It should be.
Yeah.
It should be, and it is, right? If FH is equal to mg, yes, it is 0. And that's why we are moving. Yes, we are moving, but with constant speed. There is no net force, there is no net acceleration.
But what about the negative?
FH, if I sum this with this, since this number is equal to that, they cancel.
If you're summing them, then wouldn't it be 2D?
But this is plus and this is minus. So if I sum this one with this one, 0.
So you wouldn't sum FH cosine theta minus mg cosine theta and then sum with these. You would do the whole thing together.
The network is FH cosine of theta d minus mg cosine of theta d. This is the network. And we said that this one is equal to that one, so it's 0. Okay, so everything is going in the right direction. But I haven't done yet what my question was in the beginning, which was, what is the work done by this FH? What is the number? Okay, this value for the FH I know because they give in the mass, so I can put just mg here. I know that. But they didn't give me the angle. They didn't give me d.
You can use H.
Yeah, I can use h. I can use h. How? So the problem for me is this, which is also showing up here.
Height. That's
Oh.
How are these people coming up with this idea of using the height? What is in their mind? What I wrote there is this d is the cosine of this angle. But the problem gave to me this h. Let me make a triangle here for you and tell me
It's 90 degrees.
what you think.
Can you say that that's 90 degrees?
Yes, exactly. This is 90 degrees.
It's the left hand
Yeah.
of L over H.
That is a triangle.
Yeah.
Yes.
Wait, the reason that we. Oh, okay, never mind. I'm sorry.
Okay. So here I have a triangle. In this triangle, I have this symbol for the hypotenuse. I'm calling D, the hypotenuse. I have this symbol for this angle. And I have this side that is H, and I do have this H. Don't confuse this H with hypotenuse. This H is the height, okay? It's the height that is given in the problem. What is the cosine of this angle?
Which angle?
This angle theta here.
10 over D.
Cosine of this theta
Is 10 over D.
Yeah.
is the adjacent,
Over
which
the
is
hypotenuse.
10, which is the height, divided by the hypotenuse, which is this d.
Yeah, but we don't have D either.
We don't have d, but let me continue with this. Do you agree that the height is equal to d cosine of theta?
Yeah.
Okay. What is showing up in my red box there?
Cosine D. Cosine
D?
theta.
D cosine of theta. So, instead of writing d
Ah.
cosine of theta, I'll put height.
That's so smart.
And here I'll put height.
Oh my god. What? That's crazy. Yeah, I know. I'm a little blown away right now. I'm a little overwhelmed.
You first you look and you get desperate. No, I don't have the angle. I don't have d. What I'm going to do? Stare for a while, and then you see that there is a relationship between the d, that angle, and the height. So, with the FH and with the height, we can get a number there.
Except that we don't have theta.
But we don't need
don't
theta.
need theta.
We need the height.
Replace the whole cosine theta.
This
D
is going
with
to
height.
be m is 15,
I know. Isn't that
g
cool?
is 9.8, and the height is just 10.
So cool.
What are we trying to find?
We
You're
want to find
overwhelmed,
this
right?
number.
It's so cool.
What are we trying to find now?
We want to
You
find
know
this
how to
word.
work.
Okay.
So
Okay,
for
now I have to use the
finding the
height.
word, I'm fine.
Figure out.
Yeah, I
D
know.
cosine
And
theta.
here's the same, but with a minus
Also, I'm
sign.
too
Minus
afraid to just
15,
place stuff.
9.8. Got it? So I can find the numbers, even though I don't have the d, I don't have the angle theta. No, I have the height. Yes.
We also don't have FH, but we know what it is because we know it's the opposite of mg. Or okay.
We do have FH because of what is said in the problem. Constant speed, I know those forces are canceling, so I know they have the same magnitude. Okay? Now if you look at this work, how we computed this work, now what do you conclude? You see, there are sort of two ways to find the work. Either what I did for finding that whole equation, what I did is I have that force, I pick the component along the displacement and find the work. Or, what am I doing now? I have the force here, I pick the d and get the component of the d along the force, that's the height. So you see that at the end, this work only dependent on the height, only depend on this displacement.
So you can do d cosine theta.
Either we do f cosine of theta or I do d cosine of theta. It's the same. What I need is that these two guys become parallel. That the force and the displacement are parallel. Which one I'm going to push in the direction is up to me.
Oh.
Yes.
What would it look like if we did do the opposite way? Like, how would we write it out?
That's exactly what is going to show up. D cosine of theta. I started by doing f cosine of theta multiplied by d. Now what I'm doing is f d cosine of theta. It's the same equation. Let me explain again. Let me see just here. Okay? How I find the work? I put the force cosine of theta. So this I'm decomposing the force, multiplying the displacement. Or I do the work is the force, and now I decompose the d. It's the same thing. Either I decompose the force, I put the force cosine of theta, or I didn't touch the force, I decompose the displacement.
But it won't always be cosine. It could be sine.
No, for this angle here, to put the angle between the two is theta. So it's
With a different, probably different angle. We'll solve that equation, but it would be cosine.
they could try to confuse you, but you're going to look at the angle between the two.
So it usually.
So it's a cosine because it's the angle between the two.
Is there ever a case where it's not cosine?
It could be not cosine. But they could have told you instead of this angle, they could have given you this angle here. So then you would have to find that one. But okay. What I want to do now, this is a question about the qualitative question. If the Earth do work on the moon, see Earth, the moon.
I'm already doing like that.
So let's make a drawing and see if we understand.
Oh, network.
Network, yeah.
Okay. No, probably not.
Well, because they're both falling at the same rate.
So we have Earth here.
There's no overall.
We have the moon here. There is a force between them, okay. Here is this force. The force on the moon, okay. But where is the displacement of the moon?
Which one is the moon?
What's the moon?
The moon is here. This is Earth.
It's
Okay.
perpendicular to
Yes.
Earth.
The displacement is always perpendicular. It's always tangential. So then you never get a network. It's just a tricky word.
Say that
I missed
again.
that, sorry.
So this is the force, but the moon doesn't follow this force. Otherwise it would be hitting the Earth. What the moon keeps doing, rotating, so the motion is always perpendicular. See? Because it's tangential.
Right.
So,
Uniform constant velocity.
yes, this also, but for this force, for this gravitational force, it's perpendicular. They're always perpendicular. You see what I'm saying? This is the force. If there was displacement along the force, then the moon would be falling on Earth. then yes, there would be work. But there is no work. The moon just keeps moving tangentially. So the angle between these two vectors, the displacement and the force, is always perpendicular.
And perpendicular work is not considered work.
Then the force is not helping us that displacement. Right? It's just like the box here. The Fn, the one was bringing the box to the right. That Fn was not helping for that.
But this is assuming that the orbit's a perfect circle. Since it is an ellipse, then in actuality we would have.
Still, at this position, they are still tangential. No, so the displacement is still tangent to your ellipse.
Even though there are times when the Earth and Moon are closer and further away.
But remember, the work is the force has to be along the displacement. If the displacement of the moon was along the force, it would be moving in this direction. That's when you would have work. Okay, this is the moon. The only way that this force would be creating work would be if the moon was moving here.
Well, it does a little bit if we're saying that the orbit is an ellipse. There are times where the moon is closer.
Yeah. Like this week, isn't that a
The
whole big thing
supermoon?
this week?
Huh?
The supermoon.
The supermoon,
this
isn't
week.
that the whole big thing this week?
What? What is?
You're asking us
Did
to
you see
explain
it?
astrophysics in like 5 minutes.
Actually, though, did you see it?
No, I tried.
I think like when you're
Yeah.
pulling the box, it could be getting
I
closer
didn't know
to you, but that perpendicular force is still perpendicular. It's not related.
Yeah.
So maybe like the moon is moving closer, but the force is still that.
But not because of that force there. Yeah. It is true what they are saying that there is this ellipse that it changes the orbit, but the displacement is not. It's not falling on Earth. That's what I'm trying to say.
Just nothing happened. What I'm confused about though is that the shape of the orbit, the displacement is in the curve of the orbit. It's not.
The
It's
displacement is here, right? So,
yeah,
but
it's not flying off tangentially. It's
No,
following
but
the curve of
exactly at this point, this is the displacement. Exactly at this point, this is the displacement. So if you go point by point, they are always perpendicular because it keeps rotating. Okay. This is a nice conceptual question. This one, yeah.
Don't they have to watch? Didn't they
No,
just
they would only do this if it's following.
Yeah, not the moon, right?
because they can't be parallel. to each
Yeah,
other.
the force and the displacement of the moon is not parallel. The moon keeps moving in this circular motion. It never falls on Earth. Okay, this is just something that will be useful later. You don't need to get scared of what I'm going to say because you're not going to use it. But in these cases where the force is constant, when we wrote this equation that the work is the force multiplied by the displacement, so that this force was already parallel, okay? I could make a drawing and could make a plot of that force versus the displacement. So, if I went, let's say, from this position here all the way to this position, I would say, okay, so this is my displacement. And if throughout this displacement, my force was constant, it had, let's say, this value here. So this is the value of my force. Do you agree that what we wrote here is just the area of this rectangle? Is the force multiplied by this displacement?
Yeah.
Okay. So the equation that we wrote for work is just the area underneath this value of the force. Fine.
Okay. So we can use it to find the area under a curve?
So the area in this drawing is the work. This is very important for physics students because sometimes they have problems where the force is not constant. The force keeps changing as the object goes on moving. So what they need to find is the area of this funny figure. When they find this area, they get the work. For those who ever heard of calculus or had any class on calculus, the area is what is called the integral. Okay, so to find the work, you do the integral of the force along this displacement. You don't need to know that. We just try to remember that there is this area involved, and we will use it later. Oh. Now comes yes.
This one, like, you said if there's no acceleration, there's no net force, no network.
If there is no acceleration.
But like on a graph, if you're changing distance and displacement, you're changing force, this interval.
You I may be moving. The displacement is here. I am moving, but my speed is not changing. So there is no acceleration. So that's the same problem here. But wait. This is not the same problem. It's totally different. Here I do have a net force. So now I don't understand what is your problem.
Like let's say if it, like the one we just did where there was no acceleration.
The height, right?
Yeah.
Okay.
So there was force up the hill, right?
There was a
Force.
for the
And
height.
there was a displacement.
Okay. There is the work. If I put a there is work done by just this force. So there was a work done by just this force, and it's this force multiplied by the displacement. There is another work done by this force. Okay, and this is the force with the displacement. That's true. If I only look at this force, but if I look at the net is the sum of all of these forces. The net force cancels, and the net work therefore is 0. But I may have individual cases. Okay? It's like it's like even chapter 4. I have a force here, but I have another force equal there. They cancel, but individually they exist. Okay, energy. Yeah.
For the graphs on the left, is it like a constant force?
In this case here, yeah, the constant force, you see this number here never changes.
Yeah.
Here it goes on changing. Okay, so let's go then and start talking about energy. You heard about energy throughout your life, right? It's an idea that you take for granted. Energy is always conserved. You hear this over and over and over again, right? If anyone, if a scientist comes with a new theory and they check and the theory predicts energy is not conserved, they just throw away the theory and throw away the scientist. That's like, there is no way. So energy is always conserved, we keep saying that. But what does it mean? There are many different kinds of energy. So, examples of energy. Have you heard about kinetic energy? Mm-hmm. What is kinetic energy for those who heard about it? Half of mv squared, for those who already know the expression, but what is important here is the v. So,
Moving.
energy of motion. So whenever you're moving, you have this kinetic energy. Okay. But sometimes I'm not moving. So what happens to my kinetic energy?
It's 0.
My kinetic energy may be 0, but this energy is in another form. For example, here I have my box, and it's high up. It has what we call potential energy. It has a lot of potential energy, gravitational potential energy we call it. What is this potential? Potential for what? Potential to do work. Potential to give me displacement. If I let it go, what will happen? It will fall. So this gravitational potential energy will start decreasing, starting getting smaller and smaller. Will it disappear? Well, the gravitational potential energy may disappear, but it will be transformed into kinetic. So there is always this exchange, this transformation from one kind of energy to the other. The total, the sum of all the energies involved is what we say that is conserved. Okay? All right? And now I see people already like closing their eyes.
We're just not ready to see it yet.
It's the middle of midterms.
Yeah, something is going on. The other group also is like, okay, what else?
We haven't slept in a week and a half since midterm started.
But then
I
after
haven't
the
really
break,
had
after
midterms.
Thanksgiving, you come back with a lot of energy, yeah, because there is much more to learn.
Oh boy.
Or sleepy from turkey.
Yeah. Okay, so what is this story? We are going to be talking today just about what we call mechanical energy. This is one category of those energies and includes the kinetic energy that we're talking about, the gravitational potential energy, and I'm going to mention to you another kind of potential energy which we call elastic. Elastic potential energy. What is this one? It's already the following. If you ever played with a spring with a coil, if you let the spring there by itself, okay, it's happy. But if you stretch the spring, it acquires potential energy because if you let it go, whew, it moves. Or the other way around, if you compress it, you let it go, whew, it wants always to go back to its original length, to its original length. Okay? So this is what we call another kind of potential energy, elastic potential energy. So we'll talk about these ones today, but there are other kinds of energy. See some showing up there, heat energy, nuclear energy, and chemical energy. Okay, energy is not destroyed, it's only transferred.
So let's say with the elastic energy, that energy would have to come from somewhere,
Yes,
like from nutrition.
yes. I have to eat, be strong, right? And then I have chemical energy that can be transferred to my muscles and so on, so I can compress that. Then when I let it go, so I gave this potential energy to the spring, then I let it go, this potential energy it becomes kinetic because it's and that's how
What's the
it's this one. When I put the box high up, because of gravity, it has this potential. If I let it go, poof, it will fall. So
Were you giving it potential initially rather than raising it up?
yes, I have to be strong because not everybody can. You have to be strong to give energy to bring it up, to overcome this gravitational potential. And now I let it go, shoo, it comes back. Okay, so let's talk about what the other was telling us first. What is this kinetic energy? She already said the expression is 1/2 of mv squared. Now comes a little maybe boring part for you, which is I want to derive an equation for you that combines that connects the kinetic energy that I just wrote here with work, with net work. Okay, so be a little patient and let's discuss this a little bit. Huh?
We discussed this in chemistry.
Of course, because chemistry they just use everything from physics.
Oh,
Is there
Physics is the most
fired.
basic one. What do they do? Put two atoms, then they get a molecule. Don't tell this to Dr.
Internet.
Huh?
It's going on. You're on record.
No, she
rap
doesn't.
battle.
Yeah,
He just wanted to teach us AP physics because he's like, everything's just physics. So at
They
the end
are.
of the year, we bought him
See,
first
someone
year.
There's
was
like
you.
Dr. App in the beginning, she always says everything is chemistry, and then everyone says everything is biology. Like,
Well,
You should fight it out.
but if you go beyond, okay, everything starts with the cell, but then you go to the molecule, and then you go to the atom, and then you go to the electrons and the protons and the quarks. That's physics. Anyway.
So we
No,
study
no.
it backwards.
Physicists are super arrogant. Physics, yeah,
They all work
believe
together.
So we should start then physics and then do chemistry.
No, that's
and
what
then
my
biology?
ninth grade biology teacher believed, that we should do physics first, and then chemistry, and then learn biology because it pulls from both of those concepts. If you really want to learn biology in depth, and if you really want to learn chemistry in depth, you have to know physics, and if you really want to know biology in depth, you have to know chemistry and physics.
And if you want to know physics, then you
Like
have to know
biochem,
how.
kind of.
So like
Yeah.
Yeah, then you never end. No, the methods are different for each of these different stages. The physics law that you use are different for different stages. Okay, coming back to some break, some distraction, coming back to the derivation, we cannot see. Okay, so here we have a truck, and to make it more fun, what is the story? The truck has this initial speed because there are a whole bunch of people pushing it. Okay, so we are pushing it.
It's on its side.
Yeah, we're outside. The engine broke. So we are outside pushing the truck. We start with a V1, and we managed to move this truck by this D, and here it already has V2.
Are those the wheels?
Are you criticizing the picture?
This is the light
Are you
of the
criticizing
truck.
the picture?
Oh.
Oh,
It's not on its side.
because I wanted to show the
Oh yeah, oh I
front
thought
of the
those were the
truck.
wheels also.
These are the-
Wow, now he's criticizing.
No, I just was okay with it, and you were questioning it.
Because I thought it was.
Okay, and here's the driver. Okay, and we are pushing the
You see, he's not on its side. That was the point.
So, how did we manage to increase the speed of this bus? I said truck, right?
It could be a box with wheels.
So how did we increase the speed of this bus? I'm changing our bus. We exerted this force. So there is a net force. Remember that you're asking about it. So there is a net force that is able to make the speed of this bus to change. And this net force, all these people there together, one on top of each other, so we get this net force that gives me ma along this x direction. Okay, this is chapter 4 that you already know. But suppose I don't have a, but I know v1 and I know v2 and I know this displacement d. How can I find this a?
Isn't that like
Chapter 2.
like
V
V
squared.
over D, like
Yeah.
displacement.
Okay, very good. So I know that the final, the v2 squared, is v1 squared plus 2a delta x, which is the d here. So from here, from this old equation of yours, you know that this a is v2 squared minus v1 squared divided by 2d. Okay, so I'll keep this thing also in this box. I'm going to use this later. And I have this net force. Okay. What else do I know? This was chapter 2, chapter 4. But you may not remember. What I'm trying to do is to find a relationship between net work and kinetic energy.
So work equals force times cosine.
Very good. So the work is the force multiplied by the displacement. Okay, so I'm going to write that equation that I have for the force. That equation that I have for the force is m. The a is this one, so I'm going to put this a here. v2 squared minus v1 squared divided by 2d. Okay, so this is the a and the d. Can I cancel anything here?
D.
Okay,
Well, you
very
can
good.
cancel it too.
No, how can I cancel 2?
Okay, fine.
And you're at 1/2 mv.
Someone already saw this story.
I have it.
1/2 of v2 squared minus 1/2 m of v2 squared, 1/2 of m v1 squared. Let me rewrite.
Okay.
So this equation here is 1/2, the half that you wanted to cancel but we cannot, m v2 squared, and the other one, 1/2 of m v1 squared. What did I find here?
Equation for work net.
What I was after. with the kinetic energy. So I'm going to put it high up here, okay? So the net work is the final kinetic energy, this one, minus the initial kinetic energy. So the net work is the change in kinetic energy. Does it make sense?
Brilliant.
How can I change the speed? If I have a net force. So the net work is the change in this kinetic energy. And this is a big deal. This is a principle, work kinetic energy principle. That the net work is this change in kinetic energy. Don't mess up things. It's only the net work, not the work of individual forces, it's the net one. Okay? Alright, so this is very simple to play with these equations. Now, you see, that's the nice thing about energy and work. It's just numbers without angles, especially energies, right? It's just a number with the joules, a number with the unit. I don't need to worry too much about the cosine, sine, and so on. And this, you're going to start seeing the advantages in these problems. So, first problem. I have a baseball, I have the mass thrown, it acquires that 25 meters per second. We want to know what is the kinetic energy of that final speed.
We're given everything, so you could just do K with
So,
that.
yeah, very good. It's even boring, right? You just need to use.
Does it have to be in kilograms?
Okay,
or
does it
can
have to
you
be in
leave it-
kilograms?
Oh.
That's the only catch. You have to be very careful with the units. If we are going to use joule, yes, put everything in kilograms.
Here, if you're throwing something, it's going up at an angle.
No, here what you can think of, you could even put this ball on the table. You're just giving it a speed, and we don't care if it has angle, if it doesn't have angle. The kinetic energy, I don't care about any angle. The kinetic energy is just that 1/2 of mv squared. Doesn't matter how it's moving. What matters is just the speed.
Doesn't it matters how it's moving because other forces, like other energy, will be acting on it. Like if you throw a ball in the air versus rolling it across the table, if you throw it in the air, only there's gravitational force.
Yes, and then if you want to, you can compute the work done by the gravitational force and so on. But kinetic energy, what we call kinetic energy, is just what is the speed.
So we're ignoring everything else.
We forget about angles, we forget about all the other forces. If they give me the speed and the mass, easy. I don't need to think about anything. Okay?
Wait, what is joules? Like when you break up joules?
I'll write and then we'll see. So the story of, okay, let me write then the story of joules first.
Kilograms
Joule is
meters
the
per
unit of energy when we talk about energy. It's the unit when we talk about energy. It's the unit when we talk about work. So work, we said, is force multiplied by the displacement. In the international system, force is Newton. Do you remember Newton? Yes? Or I can also decompose Newton. Okay? So it's Newton and the displacement is in meter in the international system. This combination of Newton versus meters is what we call joule.
Okay. And is kinetic energy also as you're doing joules?
So kinetic energy, gravitational potential, all of these energies, one of the units that we can use is this one joule.
So how do you get that from there, from mv squared?
Okay, so let's do this exercise of units. Let me put here half. This is just a number. Don't worry. The mass, I'm going to put that 0.45. 145 kilograms. So I'm isolating the unit here for you, okay? And then comes the speed, which is 25 squared. And let me put the units here. Speed is meters per second, so meter squared, second squared. This combination of units will give me joules. And she wants to double check. How do you know that this is and this is the same?
Oh, I was gonna say, kilograms meters per second is newtons times the extra meter.
Yeah. So Newton is force. Force is mass, which is kilogram, multiplied by acceleration, which is meters per second squared. So you see that this and this is the same. So that's why I'm calling this unit, and this is the same. So that's why I'm calling it. If you play with grams and centimeters, remember, anyone remember what's the name of that other unit? When I have grams and centimeters and seconds.
Dime.
Yeah, you should remember, it's a funny one. Okay, so this was what I'm finding here is the final kinetic energy, where this 25 was the final speed. Okay, so this is part A of the problem. And the number, I think, is there, is 45, I think, right? 45. Okay, so if you compute this, the final kinetic energy is 45. Part B. What was the net work?
It's the same because 0 is the
45 minus 0.
I didn't read the problem correctly. What was the net work done on the ball to make it reach the speed of 25 meters per second if it started from rest? So I know that the V initial is 0, which means the initial kinetic energy is 0. And I know that net work is the final kinetic energy minus the initial. So, since the initial is 0, the final is 45, that's why I got the same.
Why is K initial 0? Is it only the velocity in the equation? Is it referring to initial velocity or final velocity, or does it
They tell us here, see, we started from rest. Rest means 0 initial. But then we are going to reach 25.
Oh.
Yeah? One more. How much work? So the net work. The last problem. How much work is required to accelerate? They are telling me about acceleration. Do I have a net force? Acceleration, net force, yes. Okay. So, how much work is required to accelerate a car that has 1,000 kilograms from 20 to 30 meters per second? How do I find this net work?
K final minus K initial.
Exactly. K final, final kinetic energy minus initial kinetic energy. All right, what should I put there? 1/2 of the mass, that is 1,000. The final, 30 squared, minus 1/2 the mass, which is 1,000, and that's it. Easy problem, huh? You don't need to think about the directions. All right, and the number is big. That's to move a big car, a big mass. To change the speed of a big car. 2.5, 10 to 5 joules. Okay. Good. There are now 2 other definitions that I wanted to give to you. But we won't have time to go into detail, so let me just sketch. I'll sketch and then I'll try to justify as much as we can for today. So, let me isolate one important equation that we just found, that we just discussed. That's the one for kinetic energy. 1/2 of mv squared. Fine, good. This is the kinetic energy, but I said that we were also going to play with potential energy. One of them, we said, is the gravitational potential energy. So I'm going to call it P, from potential, gravitational. And the equation is mgy. Gravitational potential energy comes from the force, from the weight, from mg. Okay? So this is for each potential force is caused by a different. So let me see again. Each potential energy is caused by a different force. Let me repeat. Each potential energy is caused by a different force. So the gravitational potential energy is caused by this force here, which is the weight, the gravitational force. Okay? So it comes with the force and this y. What is this y? It's the position.
Displacement.
Is the position, okay. The value of the potential energy at each point is that position where I am, how high I am. So this position y here gives me mgy1. If I'm here, this gives me mgy2. And then you see, okay, the higher I am, the more potential energy I have. Makes total sense. But there is one catch in this thing, which is, okay, what are you going to call zero? What am I going to call zero?
Zero. You have no potential. You have no potential energy when you're flat on the ground.
Good. I don't have potential energy where I'm on the ground. But what is the ground? Is it here where my feet is on the 5th floor? Or is it the ground floor on Lexington Avenue? Or is it on the 10th floor? It doesn't matter. That's the whole point. It doesn't matter. The point where you're going to call zero, I don't care. What really matters is the difference. The difference is the height. Okay, so the height is the y2 minus y1. Why do I only care about the difference? Because how do I get work? My object is here, it falls this much. So the work comes by the difference between this potential energy and wherever it goes. Okay, so it's the difference in potential energy that will give me that displacement, that will give me the work, that will allow me, I don't know, to do the foundation of a building. No? But how do people do the foundations of the building? They have those, I cannot call it names, no, but anyway, those big irons outside the ground, right? And then they drop something, bang. And what happens is that work forces that nail, that big iron inside the ground. So the higher I put my object to fall, the more work I'll get to press that nail, that iron inside the ground. See, so all that divergence. All that to say that what we need is this difference, okay, in the y's. What we need is this height, this difference.
From wherever
To
it
get
starts
the
to wherever
work.
it comes to a stop.
Huh?
From wherever it starts to wherever it comes to a stop.
Either to a stop or suppose the story, what we said, that my potential energy will be transferred into kinetic. Okay? So here, where I was holding my box, right here has no kinetic. Suppose I wanted to know, as it falls, I wanted to know what is the kinetic here in the middle. So what I care about is this difference. Okay?
So like-
Even though it may still be moving, may not have stopped yet.
So you would just say y2 minus y1 is equals 0 when you're at like the ground, like when
Yeah.
it's stopped.
Yeah. Well, if I'm here at the ground, I have then there is no
There's
difference.
nothing.
Yeah.
Yeah.
So you're always after to get
After
work.
that.
You always after this change.
Okay.
Okay. So let me stop here, but let me tell you, and then we talk a little bit about the example. Okay. So the story is for each specific point here. I have this equation for the gravitational potential energy. But when I want to compute the work will be related to the difference. And the difference is the height, is what we care about. We'll talk more about this on Monday. Can I just give, no, that's enough. That's enough. no more equations. What are your questions about the exam? First thing, the conclusion, the decision for everybody. If you have any friend who's not here, tell her. The exam will be based on everything from chapter 5, everything from chapter 4, and chapter 3, just the end of chapter 3, the relative motion when we are trying to cross the river. Okay? And that's it. No chapter 6. So you have a lot of time to dedicate to chapter 5.
And is it gonna have multiple choice or?
Oh yeah, right, the multiple choice. So if there are multiple choices, maybe there will be. But what I was thinking is qualitative questions that are not too hard. Remember that extra PDF
Yeah.
file. So those qualitative questions, not the ones that you have to solve.
Okay.
There's some each
Like there's
chapter.
math and then there's like
Yeah.
conceptual
The
questions.
conceptual questions. In the PDF file that I distributed to everybody, it's also on Canvas. Okay.
All of them.
It's everything. So you can find all the chapters there. So for each chapter, the beginning is just qualitative conceptual questions and then problems to solve. You just need to focus on the concept. Okay? So if there is a multiple choice, it's from there. Or it could be a easier kind of problem, either from WebAssign or from the booklet, but I would write it in a multiple choice way. So even if you don't have time to solve, you could still guess.
Can we make an agreement not to have the astronaut question on the test? I keep plugging in numbers, it won't work.
I know the astronaut.
I
is
know.
correct.
spend an hour on that problem.
Yeah.
Which number was that?
But you should not. I told you.
Oh,
don't
it
worry
doesn't
about
work
the
for me.
number.
Yeah, it doesn't work.
The numbers is a mess. Like we saw with Leah today. Her numbers was 10. She got 10 hours. And it was right because the solution was 10.8, and they didn't accept. So maybe you have a very close number. If you want, we can check just so you take.
Yeah,
No, I
So-
guess
I have a question on that problem. It describes that you should use like over r, right? So that's our Earth plus the height above Earth.
Right.
If both the satellite and the astronaut have our Earth, can we just ignore our Earth and only use the height above Earth as the r?
You cannot because there are square roots, so you have to use the whole thing.
Even if we cross off the square root and it's only over r?
You cannot cross because they show up in the denominator. It's r of Earth plus h.
Right, but I think we made it so that it's like g m Earth equals r over whatever r squared. So if the squared crossed off, then we're left with only r.
Let me see just with you, but let me summarize this story, okay? So if the problem 10, the astronaut problem comes, it came before in an exam, but either I put funny good numbers, so it's a different universe, you would be able to solve, or there are no numbers. I write this equation. Can you show this equation? Okay, so it's
just
good.
how you derive it.
A derivation, a piece of the derivation of that problem. So it's good for you to know how to solve that problem. Okay, but those numbers will not be in the exam. That's for sure.
So you're gonna take like questions like last time too. Like for the long answers, it's gonna be like questions from WebAssign.
WebAssign for sure. Don't neglect the booklet. There are good questions from the booklet. Okay, be sure you know how to solve all of these problems that we already did. Okay, so let's see yours.
Thank you.
Okay, so the way you set up the equation was that you had
Comment.